chapter 4. We are still in part 1 in the sinusoidal steady state analysis. Okay, so for the 4.2 subtopic is phasor. In the phasor part, you will learn how to change the time domain into frequency domain. Where in the phasor domain, it is actually a complex number that represents the magnitude and phase of a sinusoidal voltage or current. So in here, you will have the time domain is in the form of xm. X could be the voltage. If it's the voltage, then you change it into Vm. If it is current, then you change it into Im. Okay, xm in the time domain, the form should be in xm cos omega t plus theta. And if you change this into the frequency domain, your magnitude xm, for example, the magnitude of the voltage, so Vm or Im for the current, you take the magnitude and put it over here. So in the frequency domain, your signal will be x equals to the magnitude and also the phasor. So the phasor is taken from here. Okay, this is how you do the transformation, whether from the time domain to the frequency domain, or you can do the inverse part where you can get the frequency domain, do the inversion, and you get the time domain. The concept of phasor is rooted in Euler's identity. So I think this is very basic, where you can see this in the previous subtopic. So the exponential function can be related to the trigonometric function, where your cos theta is actually the real part of exponent j theta, and the sin theta, where you have j over here, is actually the imaginary part of the exponential function. So you can do the representation of the phasor in the form of Vm, and this is the real part of exponent j theta just now. Okay, so the phasor representation can be in two forms. One is using the polar form. Okay, when the polar form is what you have seen just now, it is from the magnitude, and also you have the phase, okay, or the phase angle. Okay, or you can also represent this into a rectangular form. So in the rectangular form, you can see that this is actually the the real and also the imaginary part of the your triangle over here, trigonometry. Okay, so you have Vm cos theta plus j Vm sin theta. This is the angle phi. Okay, if you go back to the revision of the complex number, the x-axis is actually for the real number, and imaginary axis is y. Y-axis is for the imaginary number, and you can have the z is the magnitude, whereby you can find your magnitude over here using x squared plus y squared, and then you find the square root. And then the theta over here is using inverse tangent of y. Okay, the imaginary divide by the real value that you have at the x-axis. Okay, so this is only the revision, but somehow you will use this in chapter 5, where we will work into the power. Okay, so that's power triangle. So in the power triangle, you will be using these complex numbers. Okay, we go to the example 4. In this example, we want to evaluate the following complex numbers. So you're given the rectangular form over here. Two of these are rectangular form, and the other one is in the polar form. Okay, if you do it in mathematically, you can transform everything into a single form. Maybe you want to use only rectangular, or maybe you want to use only polar form. Okay, but since we are only apply this into your calculator, you just key in into your calculator. So you can always do like this, 5 plus j2 times, okay, times minus 1 plus j4, and minus 5 with the angle of 60 degrees. So from here, you should be able to get solution A minus 15.5 plus j 13.67. Okay, but if you need to do the steps, so it is better for you to do for this part over here. Since this is multiplied, so it would be better if you transform this into polar form. Okay, the same goes to here. So division, it is better for you to use the polar form. Plus minus, we are using the rectangular form. Okay, for the mathematical operation of complex number, there are 8 operations. So you do the addition, the subtraction. Okay, see here how you want to use the operation. So for addition and subtraction, normally we key in the rectangular form. You have real and also the imaginary number. Okay, for multiplication and division, you are using the polar form. Okay, and then the reciprocal. What is reciprocal? Reciprocal is 1 over z. Okay, 1 over z or equals to 1 over r. That is your magnitude. Magnitude at triangle with the face angle of minus theta, minus phi. And then number 6 is the square root. This is the square root, whereby you do the square root of your magnitude, and by doing the square root of magnitude, you actually divide the face angle by 2. And then number 7, you have complex conjugate. You need to know this because in chapter 5 there will be topic of maximum power transfer, whereby you are going to use the complex conjugate to find the load impedance. Okay, so the conjugate, the complex conjugate can be written as if you find the value as z equals to x. Okay, the real axis plus jy. So the conjugate is written as z with star. Okay, if you see this, then you know that this should be the complex conjugate of z. Okay, and the real part is same, but instead of plus, you do minus. Okay, it's conjugate. Instead of doing positive, you find the negative part. Okay, if you plot this into the real and imaginary axis, so if this is your z, okay, for example, this is your z prime or z star should be over here. Okay, and Euler identities, this is very basic. You do from the trigonometric, you should get cos phi, cos the angle, plus minus j sine the theta. Okay, 4.2.2 is the Phasor transformation. How you can do the Phasor transformation? A Phasor can be regarded as the Phasor transform of a sinusoidal function from the time domain to the frequency domain. Although the name is sinusoid, but we keep the general equation or the general representation of the sinusoidal function in terms of cos. Okay, Vm cos omega t plus the phase angle. Okay, so this is the time domain. If you have in sine, the function is in sine, please change it into the cos. Okay, change into the Vm cos omega t plus whatever the angle, and then you do the transformation. Okay, so meaning that to get the frequency domain Vm exponent j theta, you should do this. It must be in terms of cos. Okay, then only you can represent this into frequency domain. Or now you can write this down as Vm with the angle this, like that. Okay, the same goes for the inverse Phasor transform, where you actually transform the frequency domain into the time domain. Okay, remember that both are using the cos function. Okay, transform a sinusoid to and from the time domain to the Phasor domain. You do this, you can always transform the time domain to the Phasor domain, and you can always transform the Phasor domain to the time domain. Okay, so look at the representation. It must be in the, you have the magnitude, it must be cos function, and it has the angle over there. So in terms of the Phasor domain, you just take out whatever the magnitude and bring it over here, and also you take the angle. Okay, so Phasor must be defined in the cosine function. Okay, in all the studies. Okay, if a voltage, let's say you have a voltage written as Vm sine, okay, sine omega t plus let's say plus 20 degrees. Okay, for the time being, you cannot transform this into this one yet, because the angle will be different, because from here you need to transform this into cos first. So you're going to use whatever you have learned from the previous subtopic, how to change your sine function into the cos function using the trigonometric function. We go for example 5. Here we want to transform the following sinusoid to Phasor. So from time domain to the frequency domain. Okay, so you're giving the 6 cos 50t minus 40. This is very straightforward. So you already have the cos function. So we just transform this into, take out the Im. In here you should get the Im in terms of Phasor domain. Im with the angle. Okay, with the phase angle. So it should be written like this: 6 with the phase angle of minus 40. But then if you look into the sorry, this is B. B equals to minus 4 sine 30t plus 50 degrees angle. So if you look here, it is not in the cosine function. So what you need to do is transform this into the cos. But normally we only have the magnitude is positive function. So you need to change this into positive for cos 1. Okay. So we are doing this using the trigonometric function, where if you have minus sine A, it can be changed into cos by adding 90 degrees. Okay, so we have Vt equals to 4 cos 33 plus 50. This is the original phase. And then you plus 90 over here, because you want to change from the minus sine function into a positive cos function. So now you have the phase angle as 140 degrees. Okay, so now you have 4. Since this is already in the cos function, now only you change it into Phasor domain. 4 with the phase angle of 140. Right? Okay, this is for your exercise. You can work this out. How to transform this into corresponding time domain. Sorry, the question should be Phasor to the time domain. Okay, so you have the minus 10 is your maximum magnitude, but then because this is minus or negative value, so please change this into positive 10. Okay, you know that when you have this minus 10 means that is minus 10 cos omega t plus 30. Okay, this is the what it looks like in terms of the time domain. Okay, remember that whatever Phasor domain that you have, it must be in the cosine. So you write this down first as minus 10 cos omega t plus 30. Then only you change this minus cos to the positive cos, where you need to add it with 180 degrees. Okay, 180 degrees. Okay, so that's why in the solution you have 210. Okay, How about this one? Since your I is actually J5 minus J12, so we write this down into J5. Okay, multiply first, and then you have minus J square 12. Okay, so what you need to do is actually we change this into J square is actually minus 1. So you have minus 1 times minus 1. So that's why you get 12 plus J5. Okay, and then you need to change this because this one is in the rectangular form. Please change this into the polar form. Okay, in the polar form, then only you have this one as your IM. So we write this down in terms of the cosine function. IM cos the angle. The angle is 22.62. Okay, so you will get this one. Okay, 4.2.3 is the time derivative or multiplication. This is how you change in terms of the first derivative and second order derivative of the function. For the frequency domain, you get J omega V, and if you have second order differential equation for the Vm cos omega t, you will have J omega squared V, which gives you minus omega squared. Okay, now how to calculate the steady state solution by Phasor? I think this one is you already seen this in chapter 3. Okay, we assume if you want to solve the circuit with RLC components, you need to assume a solution in the form of A exponent J theta, okay, or J omega t. So this one you assume we propose a solution into the differential equation. So this is exactly what you have done in chapter 3. Okay, and then you find the constant A and B, or A1 and A2. Okay, but somehow in here, what you want to do is, this is very similar actually, given Vs equals to Vm cos omega t, so this is given as cost function. You need to calculate the current flowing inside here. Okay, so we assume the ISS, since you are given the voltage in the cost function, so the current should be in the cost function, and we are applying, if you apply your knowledge from chapter 3, so you should be able to get the L, the additive, that is your VL, and this is your VR, right? This is KVL. Okay, this is from KVL. So applying this, you should be able to get this one. Okay, you are not going to solve this solution with the sine and cos, but this one is actually to give you insight, or to give you the idea how we are going to solve your circuit by using the omega, okay, omega function, because now we are working in the frequency domain. Okay, and then by doing this, by using the cosine convention, if you try to solve all the equation with L, the IDT, and the first order differential equation, okay, from here you can going straight forward until you solve up to real and imaginary number. Okay, so solving with the necessary condition, you should be able to get this one, J omega L plus R. So we are actually eliminating the cosine function, and we only left with the j omega L plus IR. Plus R times the current. Okay, if you look into detail, or if you look much more clearer over here, this is actually very similar to the Ohm's law, where you have V equals to IR, but now the R over there is no longer R. It's a combination of the inductor and resistor. So this is named as Z. Okay, impedance. Because impedance you can combine component R, C, and L. Okay, so instead of you write down it as V equals to IR, the R now is written as I times Z. Okay, where your Z is actually j omega L plus R. Okay, a more convenient way is directly transforming the first order differential equation from time to frequency domain. So you can always write down this as L di t dt plus R. Okay, this one is the KVL. You can write this down in terms of the frequency domain, where you actually write down this as j omega L plus R times I equals to V. So if you draw again the circuit just now, you have L over there, you have R over there, and then you have L over here. Okay, it means that you have R, and over here the inductor is no longer L, but you are writing this as j omega L. Okay, where you can find the omega. Omega can be found from the input voltage, because in the input voltage you are given the Vm cos omega t. So the omega over here, we use the whatever omega given in the input voltage, right? Okay, now in this how you want to solve the solving circuit in phase domain, the first thing is you need to find, okay, if you want to work like this, it's gonna be a more longer solution, because this one is still in the time domain. So we don't want to work in the time domain anymore, because it took quite some time. Okay, you need to predict or give a solution in the form of exponent j omega t, right? And then you need to find the constant value A1, A2. Okay, so we don't want to work in that kind of solution anymore. Okay, by solving the circuit in the phase domain, it could be much easier, because every time you transform this circuit into the phasor domain, and then you can always solve this into more easier way. Okay, what am I talking about is actually you transform all the components into the phasor domain. So for example, if you have Vt, okay, Vt you transform into the voltage. If you have dV dt, then it becomes j omega V. If you have integration of V dt, it becomes V over jW. Okay, so this is actually how you transform the RLC components into the phasor. Then only we can apply any circuit analysis into the circuit. Okay, this is the phasor relationship for circuit elements. Resistor in the time domain. Okay, on the left side is the A is the time domain, B is the frequency domain. Okay, so you look into here, this is the time domain. Okay, in the frequency domain, it is written like capital letter of V and capital letter of I. So the notation of capital letter and small letter differentiate between time domain and frequency domain. Okay, for example, you have resistor. Resistor for both time domain and frequency domain, it is written as R. The only change the notation untuk V dengan I. Okay, and then for inductor, Inductor in time domain is written for the voltage of the inductor. It is written V equals to L di dt. Okay, I hope you still remember this. This is from chapter 1. V equals to L di dt. But then, since di dt just now, when you transform it into Phasor domain, it is written as J omega, right? J omega. So, if you have L di dt, then only you write down as J omega L times I. Okay? For the capacitor, in the time domain, you always write down this equation, I equals to C dV dt. So in the frequency domain, what you do is you change or transform this dV dt just now into the Phasor domain, which should be V divided by J omega. Okay, so here you write this as J omega C times your V. Okay, and then the bottom part of here are the voltage and current phase. If you look into this, the voltage should be in the phase, okay, same phase, sama fasa dengan current. If you look for the inductor, the voltage should be leading your current, and in the capacitor, your current should be leading your voltage. Okay, so voltage will follow your current, and in terms of the inductor, the current should follow the voltage. Okay, this is summary for voltage current relationship. Elements are, it could be written in the time domain as V equals to Ri, and frequency domain pun sama. In the L, the voltage is written L di dt, but somehow in the frequency domain, it's transformed into J omega Li, and Ci equals to C dV dt, and the V is written as I J omega C. So if you want to write down your I, so I equals to J omega C times your V. Okay? This is actually like example, example 7. You're given the voltage 6 cos 100t, that is your omega, and this is your phase angle. You apply 50 microfarad capacitor, calculate the current through the capacitor. So first of all, you change this into J omega C. Okay, 1 over J omega C. Okay, that's what you need to do. And then you can find the current by using this becomes ZC. Okay, so for the ZC, now we change this into V divided by your Z. You should get the current. Okay, that's all.